Hello, everyone. Welcome to MLGdańsk online meeting. Our guest today is Nikita Pavlichenko from Toloka.AI, and he will have a presentation. Topic is visible here. And Nikita, over to you. Afterwards, we're going to have a QA. If you don't mind, the floor is yours.
Okay, thank you. Yeah, my name is Nikita Pavlichenko, and today I'm going to tell you about the reinforced learning from human feedback. I'll just provide a general overview of this field, of the recent research advances in LHF, and why I'm giving this talk. So I'm responsible for LHF research at Toloka. I work as a research scientist, and I work on some LHF applications like instruct stable diffusion and open source ChatGPT that we try to develop in Toloka. And so this is an interesting hot topic because everyone talks about ChatGPT. So, and there is a reason for that because it's a very powerful model. So it's achieved really cool results on text generation. And it was like a huge step forward from just a standard GPT-3 model, and was somehow made in the dialogue interface. And the thing that makes this model really powerful is the fact that it incorporates the human feedback. So how does it do this? There are three steps in the ChatGPT training. And so of course the zero step is to train like a really large language model that just takes prompt and predicts next token. But then you need to somehow align it with human values, and you do just three steps. As the original, like this is just a screenshot from the ChatGPT blog, and the same picture was presented in structGPT paper. So first you need to collect some demonstration data, and we'll cover all these steps further. Then you collect comparison data, and three, you use reinforced learning to fine-tune the model based on your predicted rewards. So we hear some words in this. We see some words in this on this picture. So, and the first thing I want to tell you about some recap of reinforced learning. So I think a lot of you guys are familiar with reinforced learning. Just let me give you a quick recap because it's like important to know how reinforced learning transitioned to reinforced learning from human feedback. So first, just real motivation is we want to teach a model to do some actions in some environment. And like the most common example is playing computer games. Because they are interpretable, it's easy to implement some model playing computer games because model computer games are actually on a computer. So we have a great simulator for this case. And most importantly, we have a well-defined reward. So agent needs some goal to achieve. And if you play computer games, your goal is to achieve the highest possible score. So it's pretty straightforward. And some just definitions. I know that I hope that almost everybody are familiar with them, just to make sure that we speak in the same language. So in reinforcement learning setup, agent does some actions that discretize in time. So it means that at each timestamp, agent observes some current state. Like we can denote it as t. It can be current coordinates, what is showing on the screen, etc. And at each timestamp, the agent should do some actions based on the state. So according to some policy. So our goal of our neural network, where deep learning comes, is to provide a policy that shows which actions we need to do in the current state. And the goal of the agent is to maximize the reward it gets in the episode until the episode is called some sequence of actions and states that continue until the environment stops somehow. For example, a car crashes, game ends, or something like that. And in real life, it's not so easy to define the reward. Sorry for typo here. But in Atari games, just the score. But in reality, we must do some reward engineering that will then define how good our agent will perform. And what is important to know that in reinforced learning, we have some pretty standard baselines that almost every RL application uses, and it's called proximal policy optimization. So of course we can use some pretty basic baselines. For example, sample like a lot of state action pairs, compute the rewards for all the states, and choose best actions, and then change our sampling policy that defines the probability distribution over the agent actions. But state-of-the-art methods use something called policy gradient methods, and proximal policy optimization is some kind of policy gradient method. And we need to know that this kind of optimization is really difficult, and oral optimization and RL is difficult for many reasons, because it is non-stable. It's really hard to code in, for example, PyTorch if you tried it, so you know it's a huge pain. So everybody just uses some implementations of PPO. So, and if you see these 3 letters PPO, you can see them in a lot of OpenAI papers. You know, this stands for proximal policy optimization, and some smart method for solving RL tasks. Okay, and why reinforced learning might need a human feedback? As we said before, we know that what RL is and what algorithm we need to use. So basically, the performance only depends on reward engineering. So how good we will define the reward. And if you think about it, it's really difficult in a lot of situations to define a good reward function. So because we have in mind a picture of what the agent should do. For example, here on the slide, you can see the Hopper environment, Hopper robot doing a backflip, trying to do a backflip. And you can see that it really doesn't succeed in doing a backflip. But we know somehow that it should be like something like that. Yeah, it should do some kind of a backflip, but we cannot mathematically define a reward function that if the agent will maximize, it will succeed in doing backflip. So it's really hard to derive a formula. But yeah, we as humans, we can judge which trajectories is just a sequence of state and actions. So you might think about a trajectory as a video of what agent is doing. So here you see 2 trajectories. And you can ask humans to look at the 2 trajectories and choose the best one. So the best one, it's not like should be like a complete backflip, but you can try to judge them, try to ask them to judge which behavior is close to the desired one. Okay, then you can train a separate network that predicts how good the action is in each state. So you have a separate neural network, R with a hat, that takes state and takes an action and just predicts a real value of how good this action is in this state. And then you can just train it on something like cross entropy loss, so pretty much the standard setting. And finally, you can use these predictions of the separate neural network as your reward function. So you can then apply the PPO. And these are plots from the original reinforced learning from human feedback. It's like something like called deep reinforced learning from human preferences by OpenAI and DeepMind. And there on this picture, there are some trajectories loss curves or reward curves of agents trained on different reward functions. For example, the real reward is just these are robots that were trained to walk. Yeah, and real reward is just a number of meters that agent walked. and you can see that when we train rewards, agents start doing something useful faster. We need less compute time to force the agent to do something useful. And overall, the overall results of the agents trained on the human queries are better than the reward that is calculated by the distance walked from the start. So why? This is because when you only start to train agent doing something useful, the agent just does completely random actions. And for example, if you can say that, imagine that agent just moving hands or moving legs, and these two behaviors lead to zero reward because the agent just moving legs or moving hands and doesn't go anywhere. But as a human, you know that moving legs is somehow better than moving hands, right? Or moving arms, because moving hands will, with higher probability, will lead you to actually walking. So this is why the agent starts doing something useful faster, and this is why it could succeed the better results. Okay, so this is how human feedback has shown its importance in reinforced learning, like classical reinforced learning on playing Atari games. But reinforced learning, yeah, can be applied not to just walking robots and Atari games, because like if you're a machine learning engineer, you don't care about Atari games or walking robots. You care about actual like business problems. And there is a wide range of possibilities to apply reinforced learning for natural language processing. For example, it is pretty standard technique to apply reinforced learning for machine translation. And this is because you can think about machine translation as a reinforced learning task. See what the model takes as an input. It takes some source text, for example, in English, and this is a state, yes? And it then takes some actions. It generates words. And for these actions, the model gets rewards. For example, you can think about blue score. It's just a standard quality measure in machine translation as this kind of reward. And then you can iterate through multiple source texts and generate translations for them. And using policy gradient methods, you can estimate the gradient of the reward function, not of the like cross entropy loss that you use in machine translation, but you can just derive the gradient of a blue score. And usually it's done as follows. You train the model of standard pair token cross entropy, and then you some kind of polish the model with reinforced learning on a desired metric. So first you have some relatively good machine translation model, and it performs somehow good, but you want to maximize the desired metric, and then you apply RL. And it's a common fact that blue metric is bad. So there is a lot of papers on this fact proving that blue is not correlated with human judgments, and there were a lot of attempts to introduce some better quality measures, but mostly nobody in the natural language processing community uses them. Everybody just uses blue and human evaluations, and all the people know that human evaluations are good because blue is somehow synthetic metric, some strange score. But if people say that this translation is better than this one, so like it's a ground truth, right? So the idea is, what if we can learn the reward function from human feedback first, like we did in Atari games, and then do RL? And and this is what actual structGPT paper introduces. So it just uses as a base large language model that is trained on a large text corpus, usually just a raw web crawl. And these models are capable of few zero-shot learning when you just pass the context and you provide some examples, and then the model can generate some relevant answers without any like weight updates to gradient descent. And training to predict the next token based on the internet is different from the desired objective, like follow the human instruction carefully and safely. Because if you ask some question about, like, I don't know, about the nature, for example, you don't want the model to generate the response based on some strange Reddit thread from 2002, and you want the model to actually answer your question. This is why we might want to apply LHF to GPT-3 in order to make it follow human instructions. So first, you collect some demonstration data. You just straightforwardly ask human labelers to provide some prompts for GPT-3 and to write the desired output behavior. You collect like a lot of these prompts and a lot of desired behaviors. Or, for example, OpenAI uses prompts from their applications for their API usage from the actual clients. And then you just fine-tune GPT-3 in the supervised setting on these texts. So just fine-tune as a language model, and that's it. Next, we have step 2. You collect comparisons data and train a word model. So you have a corpus of prompts, and you can generate several model outputs for them. For example, A, B, C, D. Okay, 4 different outputs. And then you ask humans to rank these outputs. For example, you can just ask them directly to rank them, or you can run pairwise comparisons and compare one by one, and then infer the true ranking. Or you can just ask them to assign a score for each output and then sort them. So as a result, you only want to get like this ranking. And after that, you can train a separate word model, as I described on the slide with Atari games. And this model is usually relatively small. For example, the main model is GPT-3 in structGPT paper, but the reward model is significantly smaller, like a couple million parameters as far as I know. And when you have this reward model, you can optimize the rewards the model gets using PPO and reinforced learning. So you sample the prompt from the dataset, you predict the reward using the reward model, and you take a gradient and optimize these large GPT-3 models. All right. And there is a discussion, for example, on Twitter about the relevance of each of these steps and the importance of each of these steps. And the consensus is that you maybe don't need the reinforced learning all the time, but you definitely need human feedback to train, like instruct generative models. So why human feedback is important? Why we can't fine-tune model on good examples and that's it. And there are several reasons why. The first thing is you need to, in order to collect this demonstration data, you need to ask humans to actually write texts. it is very difficult. If you try to run some crowdsourcing annotation project, you know that it's really hard for humans that complete the small tasks to write long texts. And for example, structGPT was trained on very creative tasks. For example, write a poem on the desired topic. So, and you need to ask like crowdsourced workers to crowdsourcing platform workers to write an actual poem. So it's in a lot of cases is not feasible, and you need some expert annotation, and it's expensive. It's just hard. So you cannot get really huge amount of data for the first step. Yeah, so it's extremely expensive and hard. And the second point is really interesting because when in this setup, when you just collect good examples, the model doesn't know that the bad examples are bad. And you can think about providing bad examples as some kind of augmentations, because in other case, nothing stops the model from generating something relevant from its memory, and just 50% generating some good outputs, and other 50% generating something relevant. And why supervised pre-training is important? Why can't you just collect preferences and train reward model and do some RL stuff? Because RL suffers from low start. In the beginning, reward doesn't increase at all for a long time and stays on plateau. And longer it stays in plateau, more compute resources we will spend. For example, like GPT-3 model training is really expensive. And you don't want that. You don't want the reward to stay on the plateau for a couple of weeks. And the last point is that model can generate outputs that are completely different from the desired ones. And in this case, it's difficult to collect human feedback and train the reward model. Because, for example, you show the workers, okay, so let me just, yeah, my dog tries to hurt my cat, so yeah, I need to stop her. Yeah. Okay, so if you show two relevant examples to crowd workers, they cannot choose the best one. And it will mean that your data is a complete crash. And you cannot get the reward model working because you cannot train like a meaningful model on the data that is complete crash. So supervised pre-training is important, and collecting human preferences is important. So both two steps are important. And there is a debate on reinforced learning stuff. So because some of the recent papers try to avoid reinforced learning because, as I described before, reinforced learning hard, and it's not stable, and like it's just computationally hard, and it's hard from the engineering side. And besides structGPT and ChatGPT, yeah, so ChatGPT is just a version of the structGPT trained on the dialogue data. And we don't really know the details because OpenAI didn't publish any paper about ChatGPT. So we can only assume that it was trained on more data or more human feedback for a longer time. And there is a wide range of possible LHF applications. For example, if you work on any type of generative model, you can apply LHF for it. Because usually when you train generative models, you train a large model on a huge data set of unlabeled data that you, for example, scraped from the internet. And in this case, the model can become misaligned. It can just produce some strange stuff. It can be biased. So you need to think about the model safety, and incorporating human feedback really solves really can be a solution for all these problems. and also can introduce some very different wide range of possibilities, what you can do with generative models. So for example, you can try to teach the diffusion models to generate aesthetically pleasant images. This is one of the things that we at Toloka try to do right now. And for example, if you training a text-to-speech model, you can teach it to use, for example, desired intonation while generating the speech. And you can do this in the previous standard steps that we talked about before. You can try to collect some demonstration data, and you can generate different voices and then ask people to compare them and choose the closest one from the design. And for the diffusion models, there is like a recent paper. There is a recent paper from Google Research that they applied when they applied LHF to stable diffusion. And if you play around with diffusion models, that you could notice that they very often they generate just wrong images, because if you ask to generate, for example, a face or a human, you can get an image of human with 3 hands, 15 fingers, or something like that. And this happens because the diffusion model is trained on a large data set of unlabeled images just straight from the internet. And you cannot train a model to generate images perfectly. It will do some mistakes. But for example, if you generate an image of a tree and the tree doesn't have like a perfect number of leaves, I think you pretty much good with it. But if you generate a face and the face has 3 eyes, I think that it will be really noticeable that it is a bad thing. So we as humans pay more attention to one kind of errors and less attention for other kinds of errors. For example, we are very sensitive to imperfections in human body, face, or something, some like human features. This is what developed in the evolution of humans. So Google proposed to solve this problem with LHF, and they they tried to solve the counting problem when the model generates wrong number of things. Color problem, for example, if you try to generate a green dog, so the model should really draw a picture of green dog, even if it is ridiculous. And they solve it with the standard LHF technique. So you train a reward function, you collect a data set of images generated by a model, you ask humans to compare them and choose the best one, or in this case, they just used a binary feedback. They just checked if the image correctly represents what is written in prompt. And then you train a reward model that just takes an image, takes text, and tries to predict if this image correctly represents this text. And technically, they just took clip embeddings of an image and of prompt and trained a small neural network on top of it. And you can see, and finally, they just fine-tuned the stable diffusion using the predicted rewards. And you can check this their papers. They say it's called aligning diffusion models with human preferences, something like that. I can send you a link in the chat later if you want, if you are interested in it. And this paper presents really impressive results. And finally, the final thing I want to share you share you is LHF challenges. And most challenges just lay in the data collection pipeline because, as I said before, data collection and quality control, especially in data collection, is difficult. And what makes Instruct and ChatGPT good are creative tasks and expert annotation. And these both are difficult and expensive. So this is what we at Toloka try to solve. So we want to make it cheaper and accessible to like small companies, and you won't need a huge budget like OpenAI to just hire expensive experts on Upwork and that stuff. So I think it's pretty much it from me. If you have any questions, don't hesitate to ask them.
I can start. You mentioned something that caught my attention about adding bad examples as augmentation. Can you comment?
Mm-hmm.
Can you comment a bit on that part? What you
Yeah, sure. Okay, sure. Okay. All right. So when you try to train a model, you want as much data as possible. And for example, you have only two types of data, like good examples and bad examples. And if you train only on good examples, you lose the other half of the data. So when you use both good and bad examples, you can just like double your data set in size. And you cannot just fine tune the model on bad data because it will produce like bad responses. So using reinforced learning, you can incorporate that feedback from bad examples, right? Because the model will know that for these bad examples, it will get like way low rewards.
I have a question about one of the previous slides, one of the first slides actually. There was a slide about comparing reinforcement learning from human feedback with some with the kind of more classic. Oh yeah, this one.
This one.
Yeah, this one. And so I think you're saying that overall results with human feedback are better, but does it really, like, do the plots actually say that? Because as far as I can read that, the violet curve corresponds to human, like, performance with human feedback, and it's actually highest in one of the plots, but not the others.
Yeah.
So if you take Walker, for example, the top Walker, you have the violet is like almost like the second from the bottom.
Okay. So these plots, usually you can just, you need to compare with the real reward, is orange thing. And you, of course, you won't see like amazing results all the time. So for example, in Reacher, when you train with the real reward, the model becomes better. So here you can see just synthetic queries when the authors try to train a reward model on synthetic comparisons. And usually doing this allows you to achieve better results than using like real reward function from the provided by environment, but not all the time. And you can see that they collected really like long quantity of human queries, so only 750, so it just very low amount of human preferences. And yes, so if you could collect like 140, the results would be better. So, but generally, incorporating human feedback is good, but yeah, not all the time.
Right. Okay. Thank you.
Yeah, and it's true. Even it's more true for like synthetic environments, like planetary games and robots. Yeah, because in this case we can define reward. So, like we can do some reward engineering and try to learn the reward, but the standard rewards are pretty good, because if you try to walk, if you just use the distance from the start, for a starting point as a reward, it makes sense, yeah, right? Because finally optimizing this reward function will lead you to moving forward. But in more complex tasks, just defining reward by your hands is not feasible at all, because just it's very complex. For example, how would you define the reward in structGPT? So
yeah,
your reward over thousands of parameters. Okay.
So I think we have 2 questions in the chat. Can you see the chat?
No, it would be great. If
okay, so I can read the
upload.
questions for you. I can read the questions, no problem. So the first question from Tomasz is human feedback crowdsourced, and is it possible?
Yeah, sure. Let me just go to the slide. Yeah, human feedback is in the structGPT paper. It is partially crowdsourced, partially not, because they used, as far as I know, Scale.AI to collect human feedback. So it's kind of crowdsourced, but they also used demonstration data from experts to train their model. But of course, it can be crowdsourced. So pretty much step 2 is really simple from the crowdsourcing perspective, because you just need to compare 2 things, and almost everyone can judge what is better. That's what output is better. And it's a pretty straightforward crowdsourcing pipeline for taking this kind of data. So OpenAI, I think OpenAI did it. So they use Scale to collect the feedback, and everyone can do it. So it's like there is no rocket science in collecting comparisons data, but it can be tricky to collect demonstration data. But you can try to balance between the amounts of data you need to collect in step 1 and step 2, because if obtaining demonstration data is really expensive, you can stay more on plateau in step 2 and just collect more preference feedback. All right? Yeah.
Right.
Please.
And another question is from Arthur. He asks how to make faster reinforcement learning for parameter calibration. Which parameter makes slower reinforcement learning?
I have no idea actually. So because it's like very very technical question about reinforced learning. So could you please elaborate what you say about it? What do you mean when you say parameter? So there are a lot of parameters even in PBO. So
right. So Arthur, if you can elaborate in the chat or hit the mic, then yeah. Any other questions?
Okay, Arthur added something. So maybe this thing first. Which parameter influence in GPT to make slower, faster reinforcement learning? That's was added to the previous question. Okay.
What parameter makes faster?
Okay, Arthur, if far easier if you can speak.
Yeah, please
jump in.
Yes, hello.
Yeah, hello.
Is listening me?
Yes.
Yes. So maybe my questions can be a mistake in the formulation, but it's my idea. What then we have, for example, the GPT mechanism, and what the parameters in this algorithm are, and which parameters influence of the speed of this learning.
Okay, what parameters influence speed of this learning? So when you try to fine tune GPT-3 or just train it from scratch, okay, so I think you're saying about the step 3. So basically, what parameters influence the speed of the training? If you have better feedback, so better reward model, you will see the results sooner in step 3. So the training will be faster. So it's something you can see from one of the first slides on the plots that we discussed before. So when your reward model is better, you will train the model with RL faster. And in order to train the reward model better, you need more data. So if you one of the key parameters is the size of your comparison data set. And in step 3, you can one of the most influencing parameters are learning rate. And this is pretty much it. So also if you try to use smaller reward model, it will be also faster. And if the base model is smaller, also you'll get the results faster, but they'll be just worse. Something like that. Okay, Arthur.
Thanks. Okay.
Okay, in the meantime, Nikita, we have another question from chat, so I will read that. From Cornel. Could you explain more why reinforcement training with human feedback works fine with smaller amount of training data?
With smaller amount of training data. Smaller, you mean smaller than the comparing to what to the amount of data that GPT-3 was originally trained on, right? If it's not right, please write in the chat or interrupt me. So this is because when you train the model on the raw scrape of the internet, the model gets the general idea of the language itself, so how the sentences are formed, which words to use after the given ones. It has some general understanding of syntaxes. It tries to memorize some facts it can get from the text in the internet. But you can think about model being misaligned. So basically, LHF tries to align the model with human preferences and values. Is that just the style of its responses is not good, right? So the style of the model that is trained on all the internet data is just like the average text in the internet, but you want the model to be like assistant, things like that. So you want it to solve like practical tasks, and it's just a bit different, just way a bit different from the original GPT-3 goal. So basically, you need to write the same words, you need to form the same sentences, but just a bit of the original goal. And this is why you can collect relatively small amount of data. So for example, for this first step, I just like a couple of thousands examples. And for the step 2, it's like tens of thousands or maybe hundreds of thousands. Yeah, because you just need to slightly fine-tune the model and leave everything else the same. Okay, have I answered your question?
Great. And actually, I have the question connected to that because, Nikita, you said that in company you are doing something related to that reinforcement learning from human feedback. Is that correct? Did I catch it correctly?
Yeah. Basically, I can share from the research side. So I work in the research team. So we basically do this for research purposes, but also like it is very likely that during research we will discover some things, because RLHF is really new and nobody knows how to do this. So there are several companies trying to replicate what OpenAI did, for example, like Hugging Face, Carper, and Stability. They try to provide open source tools, and we try to collaborate with them and help them to replicate all this knowledge that OpenAI it has of their engineers. So during our research, we try to replicate some things, try some different things, and overall contribute to the field. And we hope that it will be then somehow packed as production products.
Great to hear. I mean, good luck, of course. So your main domain is NLP as well, or what?
No, maybe even we do more research on vision than on NLP right now. But when you try to do something in crowdsourcing, you usually like deal with both text and image, and you do nothing else from text and image. So we try to be competent in both fields and try to apply something for NLP, something from CV.
Okay, cool. Great. So it's so you are doing the research here. Great. I will follow you on your channels if you have Twitter or something.
Yeah, I do.
If that's okay, I would add something. So, the key part of the reinforcement learning with human help is actually people, and Toloka indeed specialize in that, and we have one of few global crowds on the market, and our platform is really a very good tool made for engineers. So if you go and try it out, there's probably a lot of things for you to take from here. Yeah, I'm Alex. I'm also working at Toloka.
Yeah, so this, because I'm trying to look at your site. So this product you're mentioning is this adaptive ML models, actually, right? This is the what you mean?
Yeah, it's more general adaptive model. So we started as a data labeling company, and right now we also provide adaptive models, including large language models, but not limited to them.
Okay, cool. Sounds great. Are you working in the cloud? If you can ask, of course, what's your backend there?
Yeah. So we basically work on Azure, but and we can deploy on any Azure the client needs. But we do not do on-premise. So if you consume our AutoML, since it requires a lot of internal interactions and human level processes, it is stored on our Azure cloud. So you can use it via API if we're talking about adaptive models.
Okay. So mentioning adaptive models, cost. We have another question actually. So what are adaptive models in few words? So Alexei, if you started that topic, can you elaborate a bit on that?
Okay, so basically we have some kind of general models, for example, for moderation of comments in e-commerce, and you want it, but you want it to be better for you. So what do you do? So you either use some standard model that most of the clouds already provide, or you go ahead and do like the whole process of preparing a model, deploying it, teaching it, and then monitoring it as well. So that is what we cover on our site in a very efficient and automated way. So yeah, probably Nikita will share a slide or two about it. And that gives us so we have like several like a lot of different models competing with each other, and the best one wins. So basically you will get like an automated way of preparing a model specific for your needs, and of course there is a human part involved. So first you need to learn what is the good result and what is a better result, and that is what we do under the hood. And then not to to mitigate the drift of the model, also it needs to be relabeled regularly on a random subset, but also if there is like a low confidence of an answer, it should be really labeled by humans as well in order to enhance the model quality even further. So that is what we do under the hood. You don't need to worry about it whatsoever.
Wow, it really sounds like quite comprehensive solution. So, whoa.
It is, yeah. We work with with the largest companies in the world, actually. So as our clients. So yeah, a lot of interesting stuff happening.
Thank you, Nikita. Thank you, Valentina. Thanks, Alexei. Great presentation. Good luck with all your endeavors, and hopefully we'll hear from each other again in the future. Thanks for joining.
Thank you.